Record. Now, I would love to spend some time reviewing, but I can't. So we're on a tight schedule. So, but I will say that last day in terms of, okay, fine, a little bit of review, but only the concept. We won't have time to review it itself. But what we did was we did 2 sample proportions. Right, we finally graduated from 1 sample proportions where we're comparing our sample proportion to some value, right? We did hypothesis testing, confidence intervals, and now we graduated and we said, well, what if I have 2 samples and I have 2 sample proportions that I want to compare? The null hypothesis can either be P1 is equal to P2, that's the one I prefer for myself, or the null hypothesis could be P1 minus P2 is equal to 0. This one is more useful in terms of looking at our test statistic and things like that, right? We're hypothesizing that the difference between these 2 proportions is 0, right? Saying that they're the same. And there were conditions and things that we checked, right? And they're all on, well, not all, but they're on your formula sheet, sometimes in disguise, right? We can build a confidence interval for P1 minus P2, right? Using the difference in the sample proportions. As long as you're consistent with your group 1 and group 2 assignments, it doesn't matter which one is which. Okay? And then we can do a hypothesis test, and our test statistic is still a Z. Today is the first time that we're going to see a new test statistic, which is hard to say for me. The difference was that the Z, our standard error, what we use is P hat, the pooled proportion, where we throw all our successes and failures into a pool, and then we can find the number of successes from group 1 plus the number of successes in group 2 over both of the sample sizes, right? So we just shove them all into a pool, and that's your pooled proportion. And that's what you use in your Z in the standard error. There. That's some sort of review. Today, we're going to introduce the chi-squared goodness of fit. Goodness of fit, it's a thing. Hey. There. So this is you want to call it chi. So this here is chi, and it's a chi-squared. Oh, that's not a pointer. That's a pointer. That's a pointer. Square test of goodness of fit. So here, this is goodness of fit. Huh? Always. And so it's a new test statistic that we're introducing. And when we use this is, well, what if I have more than 2 sample proportions? What if I have multiple samples, right? More than 2 groups that I want to compare. And so when we use this is for more than 2 proportions. You can see the theme. We started with 1 sample proportion, and then we moved to 2 sample proportions, and now we're saying, well, what if I have more than 2, right? 3, 4, 5, 6. They all get lumped into one thing. So as an example, I can't imagine thinking that this would be a good idea, but Walter Frank Raphael Weldon, so this is kind of 1900s, was an English evolutionary biologist and a founder of biometry. Biometry? anything that ends in metry is statistics. And so he's the joint founding editor at Biometrica with Francis Galton and Carl Pearson, who are kind of big wigs in statistics. So in 1894, he rolled 12 dice, 26,306 times. At that point, how do you stop? Well, that's it for me. 26,306 times? That's weird, right? He just gave up. But anyways, his hypothesis was that that maybe the 5s and the 6s are showing up more often than the other numbers. And so what he did was he just recorded the number of 5s or 6s, which he would consider a success, right? That's one way to boil it down into a success-failure situation, right? 5 or 6 is a success and everything else is a failure. And he did observe that 5s or 6s occurred more often than expected. And it kind of boils down to the pips, the holes, and being more hollowed out. And so the base was heavier. And so then the dice with the more pips on top were showing up more often. As if that wasn't enough madness, in 2009, Zachariah Labbe in U of Chicago, he repeated this experiment with machinery this time. And so he made a homemade dice throwing pip counting machine. Probably huge funding available for that, not. But it would roll the dice and then it would count, and then it would roll the dice again and it would count. And so he was able to repeat the entire experiment in about 6 full days with this machine. And so because he had kind of technology on his side, he didn't just have to focus on a success being a 5 or a 6. He said, well, what if I just count how many 1s, 2s, 3s, 4, 5, 6s I get, right? And is that distribution even? So what he found was this. So what we're seeing is if they were approximately the same, right, we would expect in the long run, and this is the long run, he did it over 6 days, and he was able to get, I don't know how many, oh, he repeated it exactly 26,306 times. That's crazy. To replicate the experiment, I guess. But what would we expect? We would expect the 1s, the 2s, the 3s, the 4s, the 5s, the 6s to be smeared out evenly across those 26,306, right? And so that's where this line is from, right? An even distribution would look like this. Oh, hello? What's up? I'll mute everyone. Okay, that's not where I wanted to go. This is where I wanted to go. So here, this is where an even distribution would look like, or what it would look like. Now our question is, well, first let's focus on this. What do we have the tools to solve for already? Well, we have the tools to compare this proportion of 1s to the expected proportion of 1/6 of the rolls, right? We have those tools. That's a 1 sample proportion. What can I do? I can boil it down to just comparing the proportion of 1s to the proportion of 2s, ignoring everything else. That's a 2 sample proportion question, right? But what if I want to take into account all of these bars, right? And I want to compare overall, is there a significant difference in the bars to where I would expect them to be if it was just an even distribution? And that's where the chi-squared comes in. And the key part of a chi-squared test is that we have these expected counts. So I'm going to have observed counts and expected counts, and I'm comparing the two. Okay? And so we rolled 12 dice, 26,306 times. And if each side is equally likely to come up, how many ones, twos, blah, 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 would he expect to have observed? 12 dice, right? So not 1/6, because we're talking about counts now. How many counts are we expecting? 12 dice. Well, 12 divided by 6. None of these make sense except for this one. 12 dice. Rolled 26,306 times, right? I don't know what that number is. It's huge. And then I'm expecting to smear those all across 6 options, right? So an even distribution. An even distribution. Oops. Across 6 categories. Which is right. Phew. So what we would have is something like this, where, okay, I've got the outcome, 1, 2, 3, 4, 5, 6, right? And then I have my observed count, and then my expected count is that 12 times 26,306 divided by 6, right? So here, this expected count is 12 times 26,306 divided by 6. And that expectation is the same for each of these categories because we expect each side to be equally likely, right? That can change, but we're learning the ropes here. So in this case, right, these expected values are all the same because we expect an even distribution, right? And so here, we expect an even distribution. What we want to know, right, is, okay, 53,222, is that significantly different from 52,612 alongside 52,118 being different from, how far is it from 52,612, right? And so we're gonna get this kind of holistic is the word that I'm kind of drawn to, I guess, this overview, right? Not just individually the counts, but overall, how are they behaving when I compare it to the expected distribution? Yeah. And so in terms of kind of at first glance, does there appear to be an inconsistency? From those bar charts, we saw, right, that, okay, these guys, the 53,000 is different from 52,000, just looking at those values, right? I'm a little bit concerned about the 53. Anything 52,000 is kind of in the realm. Now, this depends on the magnitude of your measurement, right? And so here, I'm a little bit concerned about these 53,000s because they're overpowering, Where did they draw from? They drew from these guys, right? So they'll be a little bit less than what we expected, right? Generally. And so we just want to know if it's significantly different from what we were expecting. We're used to talking about hypotheses in terms of a parameter that we're interested in. Okay? We are. And so this is a little bit different. Okay. So the null hypothesis for a chi-squared test is going to be the observed counts follow the same distribution as the expected counts. Okay. If we go to our formula sheet now, all I really give you here on your formula sheet is this. Guess I can put it here. The null hypothesis that I give you is the observed distribution equals the expected distribution. And I capitalized expected, even though it doesn't really make sense, because the expected distribution is something that you have to calculate usually. Okay. And ignore this for now, but we're getting there. Okay. And so the null hypothesis is going to be in words for a chi-squared test, which is different from what we have been doing. Okay. You always could write it in words, but it's usually too long, right? And so in general, the observed counts, so the observed distribution follows the same distribution as the expected count. So the observed distribution equals the expected distribution, right? If we think about these counts as the distribution of counts across the categories, right? Then we have an expected distribution as well, right? Which is even. Kind of boring, but still. Once you have your null hypothesis, you can negate it to find the alternative hypothesis, which is the observed counts do not follow the same distribution as the expected counts. Now, if you just wrote this, right, this is very generic. The observed counts follow the same distribution as the expected counts. That's always going to be right, right? And so I encourage you to commit that one to memory, maybe. But here, our null hypothesis is always that these two things are the same until I have proof otherwise, right? And so there's no inconsistency between the observed and the expected counts. We're still not really talking about dice or anything in particular. And I encourage you to keep it that way. It's safer, right? Not talking about the dice in particular. In fact, I would encourage you to just say this, and that's always going to be your null hypothesis. Right? I guess I could have written that here, but then I'm just giving it to you on a platter. That's boring. If we want to know if there's an inconsistency, notice that we're not going to be talking about one-sided tests anymore. Okay, we're only going to be saying, okay, it either follows that distribution relatively well or it doesn't, right? We're not going to talk about anything else. Notice another thing, we're not going to do confidence intervals. It's hard to pinpoint what we would do an interval around, right? Because now we're talking about as a whole, how do these observed counts relate to the expected counts? And we can't really build intervals around that easily. So we're not going to do that. So now we can only do hypothesis testing. So that's a plus in my books. Our test statistic is going to quantify how different the observed counts are from the expected counts with a little bit extra, right? we have to take into account the spread that we're expecting, but it's going to change a little bit. Okay, but large deviations, so large differences from what we would expect based on sampling variation, right? We're expecting some movement around that horizontal line, right, of the expectation, but not a lot, right? Not a lot of movement around that line. And so if we find that there's a large distance between the observed and the expected, then that's evidence against the null hypothesis. Okay. And so hence the term goodness of fit. It's called a goodness of fit test since we're evaluating how well the observed data fit the expected distribution. We can take it back to just the generic form of a test statistic, which is your point estimate minus a null value divided by the standard error of the point estimate. I haven't given you the standard error of the point estimate. I haven't even given you a point estimate. So we're a little bit lost still. But what we're going to do is skip ahead to here because I want to get straight to the chi-squared test statistic. So the chi-squared test statistic, let's make sure you can see it. Chi-squared, so chi is this Greek letter, and usually it's like a little chi like this. It's got a little flare. So this is chi. So chi-squared is, let's ignore the sum for just a little bit. Okay. We're going to find the distance between the observed and the expected value. That seems like a reasonable place to start, right? My point estimate, the distance from my hypothesized value, my expected count, right? Kind of drawing some connections here. But if I have the observed minus the expected, right, then the reason I'm going to square those values is because eventually I'm going to add these all up. Now, if I'm going to add up some positive numbers and some negative numbers because we're expecting, or we're going to have some variation around the expected values, they're going to add to 0. And that's not fun, right? And so we've seen that before with the standard deviation calculation, right? We had to say, okay, well, the distance from my x to my x bars, some are going to be below, some are above, right? I square them, and then it magnifies any larger distances, or amplifies, I guess. And so we're going to take the observed count. So O is the observed count, and E, let's use, is the expected count. Thinking back to that table, right? We had observed values, we had expected values. So then you would make a new column of observed minus expected. Some are going to be positive, some are going to be negative, right? And then make another column where you square them all, right? Now we're working our way through here. So you make a new column where you square each of those differences, and then you divide, make another column of your expected values, the observed minus the expected squared divided by the expected values. Let's see. Pardon?
Each row has its own?
Yes. And I'm going to not do the calculation, but I am going to copy this here. Oh, not like that. So what you would do, if you had to do this by hand, which I'm not keen on making you do, but you should know what you would have to do, right? Looking at this formula and given the observed and the expected counts, right? Then what would you do? You would make a new column of the observed minus the expected. I like to break it up into tiny increments. And so I held out for a long time, right? Closing the door. So
Squared in that column as well?
I like to do it separately. You're welcome to just do it all right away if you want, right? But I like to build it out nice and slow. And so I would find the observed minus the expected. And then in the next column, I would square it, probably fill in the columns all at the same time. So I'm not saying that you should go back and forth, but it's nice to have them so you can visualize them. And then I would build the observed minus the expected squared divided by the expected, which is just the previous column divided by the expected count, right? So just looking at the first row here, this would be 53,222 minus 52,612. Calculator here. And I'm gonna bump these over so that I can actually write it out. So this 53,222 observed minus expected 52,612 is 610. Almost bungled it. 610 squared. So I had it on my screen and then I just square it. So I'm going to fill in this column as we go here. 372,100, 372,100. And again, I'm going to fill in the final column right away by dividing this by the expected value, 52,612. So I get roughly 7.072530,982. What would you have to do next? You'd have to add them all up, right? So you would do that for each row, right? And then, so we've done the observed minus the expected, then we squared it, then we divided by E, and then to take the sum here, this is the sum of the observed minus the expected squared divided by the expected, which is your chi-squared. So you'd have to do it 5 more times, which I don't want to do because they've done it on the next slide. Okay, but it would look like this. And then we find our chi-squared test statistic. And I'm saying test statistic, why? Because that's step 2 of our hypothesis testing, right? We stated our null and alternative hypothesis. Step 2, do the test, do the do. Do the test means calculate the test statistic. And in this case, the test statistic is the chi-squared. So this means, oh, is there someone at the door?
No.
Oh, see you. No. Really calling attention to it. Okay, so K here from 1 to k. K is generic. Why? We're allowing for any number of cells, right? Any number of observed counts. So k is the total number of cells or the total number of categories. Total number of categories. Which we could also think of as the total number of proportions, right? Or groups. How many proportions do I have? I have 53,222 out of 315,672. I could convert all of these to proportions, right? I would have 6 proportions, right? I have 6 groups, 6 outcomes. And so K in this case is 6. We're going to need that because of something involved with the chi-square distribution, which is the degrees of freedom. I've said too much already, I guess, but we're getting there anyways. So we've calculated our chi-squared, okay? And so now, and we already talked about why we would square things, right? It's the same old story. Whenever we square things, it's usually because we want to make things positive, but also we want to amplify large differences, right? That's a reason for squaring. And I'll just add this here. We've seen this in the standard deviation calculation. And we'll see it again later, more times. So we're used to calculating a Z, and then we can find the probability of that Z or seeing something more extreme using the Z table or using Excel. And so now we need the chi-squared distribution. And this chi-squared distribution has a parameter called the degrees of freedom, which determines the shape, the center, and the spread of this distribution. Okay. Now, this is not accurate because this is, don't remember, because so far we've seen one other continuous distribution, which is the normal distribution. These must have been left over from the old order. We will see the T distribution and we will see the F distribution. So we've got more distributions coming our way. And so we're going to be really well versed in taking a new distribution and figuring out how it works. But the goal of any distribution is to find probabilities, right? Find the probability of seeing something as extreme or more extreme. The normal distribution, remember, the normal is the shape, but then we need to know the center and the spread, right? Mu and sigma. And so it has, technically has 2 parameters, mu, sigma, right? To determine what it looks like. So now we only have 1 parameter and it's the degrees of freedom. Spoiler alert. The degrees of freedom is going to be k minus 1, the number of groups minus 1. It's coming up later, but I just want you to see that it's not going to be so bad. So you take the number of proportions or the number of groups, subtract 1, and that's your degrees of freedom. How is that going to behave? So here, this is way different than what we're used to seeing, right? The chi-squared distribution. So we've got a chi-squared distribution with 2 degrees of freedom, 4 degrees of freedom, and 9 degrees of freedom. Okay. And they're going to look quite different from each other. 2 degrees of freedom looks like this. Woo! A ski slope. A scary one at that. Ride your chair. Woo! Yikes. Then 4 degrees of freedom. It's kind of smoothed out a little bit, right? And so it's shifting the center further out into the positive values, further to the right is the word I'm looking for. And what happens with 9 degrees of freedom, right? Now we're sort of approaching a normal distribution. It's still quite skewed because this tail keeps going and going and going and going. So a key attribute is that the chi-squared, right, can't be negative. So chi-squared is always positive. So always positive. So you can't have negative chi-squareds. That makes sense. Why? Because how we calculate chi-squared, we take the observed minus the expected, and then we square them, making all things positive, divided by the expected count, which can't be negative. And so the only way that I could get negatives is, well, no way in that calculation. They're all positive values. I add up positive values, I get another positive value, right? And so that's why the chi-squared is always going to be positive, okay? But notice how big of an impact the degrees of freedom has on the shape. Whoop, whoop. The center, right? The center is shifting more to the right as you increase your degrees of freedom, but also the spread, right? The spread here is quite tight for 2 degrees of freedom. It's a little bit wider for 4 degrees of freedom, and it's quite wide for 9 degrees of freedom, right? And so it's one of those, which of the following is false? As the degrees of freedom increases, the center of the chi-squared distribution increases as well. We just said that looks like it's true, and it is, I promise. The variability of the chi-squared distribution increases as well, right? So the spread, and it just kind of allows for more, the center is moving out to the right, and it allows for more spread. Okay. And so that's true. And then the shape of the chi-squared distribution becomes more skewed, less like a normal as the degrees of freedom increases. That's the opposite, right? The shape of the chi-squared becomes less skewed and more like a normal. So this one's false, right, as is, but we fixed it to be true. Okay. We know things about this distribution already. We know the total area is 1 under the curve, right? That's true for any probability distribution, which is what this is. So here, the total area is 1, and the area under the curve is a probability. So the area under the curve is a probability. Some things change because we're blocked here at 0. So there is no lower tail, right? It's going to be bunched up against 0, and then it's going to be moving away from 0. So the only area that we're ever interested in, as opposed to the Z distribution where we were curious about the lower tail or the upper tail or both tails, depending on our alternative hypothesis, right? Now we're only concerned about the upper tail. So the p-value, which is step 3 in our hypothesis testing, the p-value is always the area in the upper tail for a chi-squared, of course. But I think that goes without saying. There's a table, but I refuse to print off another table. I think 2 is plenty. And so what I did was I just put it on your formula sheet. It's down here. There is, of course, a bigger table. And by bigger, I mean a longer table with more degrees of freedom, but and more probabilities. But this is the one that I expect you to be working from. Okay. And so there's an example of the probability table down here that we'll use. But why did I cut it at 5 degrees of freedom? What would 5 degrees of freedom look like? You'd have to have 6 categories. That's plenty, right? We don't want to compare more than that, right? Usually we're talking about maybe 4 categories, which means I have 3 degrees of freedom, right? So what does this look like? This tells me the upper tail area, okay? And so depending on your degrees of freedom, right? In this case, we have 5 degrees of freedom, so we're way down here on this lower line. Yeah. What this tells us is that at degrees of freedom equal to 5, for example, let me move this over a little bit. I'm going to draw a generic chi-squared curve, which tends to look like this. Maybe not so weird. I'll draw my axis first. It's skewed to the right, right? There's always a tail to the right. And so, and maybe I should emphasize that. Sorry. There. That's beautiful. At 5 degrees of freedom, what this table is telling me is that, okay, if chi-squared is 9.24, here, I'll scroll up, 9.24, the area in the upper tail is 0.1. Yeah. So we've got 9.24, just drawing it somewhere. The table tells me that that area is 0.1. So if I get a chi-squared of 9.24, the p-value is 0.1. If I get a chi-squared of 11.07, that's moving further out here, 11.07. The area in the tail is 0.05. 13.39, gonna move it, oh, I need a different color. 13.39 has an area in the tail of 0.02. And then I'm running out of space, but 1509 and 16.75, right, would each have those smaller areas in the tail. Okay, what color can I use? I'll cycle through the pink again. 1509, 0.01, and orange. 16.75, 0.0005. Yikes, that's small. Get the idea. So if we have a chi-squared value that we've calculated, right, what could I do? We calculated a chi-squared of 24 point, let me grab it. Where is it? Where is it? Where is it? 24.73. So we calculated chi-squared is 24.73. what could I do? There are two routes that I could take. Both are fine. I'm happy with either as long as you explain which one you're doing, okay? Or clearly show your work. The first option is trying to map it back to what we were doing before, right? We said, okay, I'm gonna use this 24.73. This doesn't look very nice. I want to try to find the area in the upper tail. 24.73, if I follow this scale, is to the right of 16.75, right? And we've seen that before on our Z table when we were off the chart, right? Let me continue this tail here. 24.73, right? Would fall somewhere there. You don't have to draw the distribution, but you're doing the same thing by trying to place 24.73 on this number line, right? And what it's telling you is that anything past 16.75, the area is so small that who cares? It's just less than 0.005, right? And so the probability that the chi-squared is greater than 24.73 is less than 0.005. I know. It's short, writing it that way, right? But in terms of how you're going to write your p-value, so here, this is your p-value. You could say, just verbally, the probability that the chi-squared is greater than 24.73, remembering that the definition of the p-value is the probability of seeing something as extreme or more extreme than what you saw, right? And so then the p-value is the probability that the chi-squared is greater than 24.73. Well, it's just going to be less than 0.000. Sorry, I added a 0.5. So we've got some examples coming up to build this out a little bit, but that's what you're going to do, right? For your p-value is you're going to try to place your calculated chi-squared on this number line, and then you'll have some values that wrap around your chi-squared value. What's the opposite or the other direction that we could take this? I could say, well, if I let alpha be 0.05, right, I'm going to reject anything with an area in the tail smaller than 0.05, right? So then what's another way that I could take this? I could say, well, in that case, how about I just force the area in the tail to be 0.05, and I can find the chi-squared that makes that happen, right? So here, let me just add a page. I guess it's time. Where are we here? Alternatively, we could say if we let alpha be 0.05, we can find the chi-squared that makes that happen. We can find the chi-squared that makes that happen. At 5 degrees of freedom still, right? The number of categories that you have doesn't change. So once you've figured out your degrees of freedom, then that's what you have. So from here, if I force the area in the tail to be 0.05, that corresponds to a chi-squared of 11.07. So I can sketch that out. And if I'm gonna force this to be 0.05, this is at 11.07. Sort of confusingly, we call this a critical value, which we've already used in terms of our confidence interval, but the context will tell you that they're different. This is what we call a critical value. So now, if you're looking at this, you could say, well, now if my chi-squared is just greater than 11.07, right, more into the tail, then I can reject H naught. So you're avoiding finding the p-value, right? And you're saying, well, I force the area in the tail to be 0.05. And if the area is less than 0.05, I'm going to reject it. So you see how those are equivalent, right? It's just two approaches of doing the same thing. So then, if the chi-squared, and I'm going to write a little calculated underneath to emphasize that that's the one that you calculated. So if the chi-squared that you calculated is greater than the chi-squared critical, and that value is from the table, right? Then you have enough evidence to reject H naught. Then you have enough evidence to reject H naught. We could have done this for Zs as well, but it's the same amount of work, and so that's why I don't introduce it till later. But right, you could figure out what Z makes an area in the tail of 0.05, and then if your Z is greater than that, then you have enough evidence to reject H naught. So in this case, what you would say is, since the chi-squared calc, let's use just calc, is equal to 24.73 is greater than the chi-squared critical, let's use crit, which is equal to 11.07. We have enough evidence to reject H naught in favor of HA, but let's just leave it at that. Because it's more important that you either have enough evidence to reject H naught or you don't have enough evidence to reject H naught. So is that the same as the conclusion up here? Well, if we're using an alpha of 0.05 and we found that the p-value is just less than 0.005, then yeah, I would be rejecting H naught, right? Because something less than 0.005 is less than 0.05. So then I do have enough evidence to reject H naught regardless, right? Just two different ways of arriving there. So what I encourage you to do is try both and figure out which way you prefer, right? I'm going to call this the p-value approach, and I'm going to call this the critical value approach. On the test, I don't care which one you use, so just figure out which one comes more naturally to you and use that, right? And then you don't have to memorize so much. They're the same, they get you to the same spot, but just think about which way your brain prefers, right? It's always easier to memorize that way. So you do want me to memorize stuff? I do. So notice this is equivalent to the p-value approach, which found since the p-value is less than 0.005, it is less than the assumed alpha level, oops, of 0.05, which means I have enough evidence to reject H naught. Which means we have enough evidence to reject H naught. I'm not saying what that means, right? Because then we'd have to tie back to the null and alternative hypotheses. But what does it mean? It means that the distribution of how the dice show up, right? The face of the die that show, or the dice that show up, is not independent, right? We're saying that, well, it doesn't follow that uniform distribution. So there is something going on. But we've got more practice with the p-value and just the chi-squared table. And so let's see here. We've got a generic chi-squared value, just for an example. So here chi-squared is 30, and we're told that the degrees of freedom is 10. Okay, so of course there's a huge chi-squared table, but I only give you what you need. So what we're trying to find here is we're trying to find this area. Right? If I have 10 degrees of freedom on this table, I have 10 degrees of freedom. I'm trying to place 30 somewhere along this line, and notice how, of course, it's increasing as I move out further into the tail. And so I keep going and I keep going, and 30 would be off the table again, which means because I have more areas here than we do in my little excerpt, the area in the tail is less than 0.001, which is B. Good. If I have a chi-squared of 17 and 9 degrees of freedom, then I can go back to this table. Right now I have 9 degrees of freedom, so I'm gonna erase that for a little bit. Highlight 9 degrees of freedom, and I'm gonna try to place 17. Finally, I can have something that works. Copy. And then I'm gonna re-highlight that for that slide there and use this one instead. So here, my calculated chi-squared is 17 with 9 degrees of freedom. So 17 is somewhere between these two values, right? 17 chi-squared is 17 is somewhere between 16.92 and 19.68. Doesn't matter where. We would use software if we wanted an exact p-value, right? Because again, you would have to use calculus if you wanted to integrate to find the area under the curve, and that sounds terrible, so no thank you. But how can we use this? So we're between these two values, which means the area in the tail is somewhere between these two values. Now I'm being really careful to not read them from left to right. Why? Because as I move out into the tail, the area in the tail gets smaller and smaller and smaller. And so that means that I have to read these from right to left, right? The p-value is somewhere between 0.02 and 0.05, right? And so here, notice that we're gonna have to read from here between 0.02 and 0.05. Which is that one. If we wanted a more precise value, we could get that, right? But that's a pretty good estimate, right? Somewhere between 0.02 and 0.05. You can still use that. Is that less than 0.05? Takes a little bit more thought, right? But yes, it is. It's somewhere between 0.02 and 0.05. That's all less than 0.05, right? And so you have enough evidence to reject H naught, right? What's another way that you could do it? If you wanted to use the critical value approach, you could say, well, what if I force the area in the tail to be 0.05? Then my critical value would be 16.92. Since 17 is larger than 16.92, I'm more into the tail, I have enough evidence to reject H naught. Same conclusion. This is the R code, but the Excel code is similar, but we'll save that for a lab or something. We're actually running out of labs. No labs this week. Got a t-test lab coming at you. And then we've got the lab exam. I know.
What is the lab exam?
What is it or when
What
is
is
it?
it?
It's the week of November 27th in whatever your regularly scheduled lab time is.
What is it? I said, is it just an exam using Excel kind of thing?
So you don't have to use Excel under pressure. That's tough. But you do have to look at output and answer questions based on that. Now I'm being super vague because one, I haven't made it yet. And I don't know exactly what it's going to look like. But I want you to, it used to just be theoretical short answer questions, which doesn't really make sense because you've learned skills in the lab. But what I'm thinking it'll be is maybe multiple choice code chunks, right? To find the area in the tail, you would use whichever, and then you choose whichever one you would have to type in. And so you're not using Excel, but it is on your Excel skills. I am making a practice test, but since I haven't made the test, I haven't made the practice test. So you'll have a practice and it'll just be online, multiple choice. And there you go. Question, yeah.
That's like in-person.
Yeah. Yeah, just in the lab, whatever lab time you're scheduled in. Usually you can go to whichever lab, but because all of them I think are full-ish and there has to be enough computers and stuff like that. So better off just going. I anticipate the next question is, can we use our own computers? TBD. I don't see why not, but I'll talk to Susan who teaches the other lab sections and see what she thinks. She's pretty flexible, so. Oh yeah, we already did this one. So that's fine. And how are we okay, good. So we had a chi-squared of 24 point. Hey, this one says 6.7. I think maybe that's using unrounded values. I thought it was 7.3 or 3.7 or something. Let me go back. Do you guys remember? 7.3? Yeah. 7.3. Seven three? Question mark? Doesn't look very clean. Either way, we found either the p-value is less than 0.005, which is super small, right? Which is less than 0.05. Or we found that because it's greater than the critical value of 11.07, I think it was, right? 24.73 is a lot bigger than that. So then we still have enough evidence to reject H naught. So then we remind ourselves what the hypotheses were. And so either way, we're rejecting H naught in favor of HA, which means that there is inconsistency between the observed and the expected counts. Yeah. The observed counts do not follow the same distribution as the expected counts. And so, which you could make the extension that there's bias in which side comes up on the roll of a die. Yeah. And so here they hold off until now to introduce how you find the degrees of freedom, but it's really not that hard. So that's why I gave it to you earlier. So the degrees of freedom is k minus 1, where k is the number of groups, categories, cells, doesn't matter. And so that's where we got our 5 degrees of freedom. And from our little blip of a table, oops, I stopped at 0.005, but it actually would have been even smaller than 0.001 if I had extended the table. So here from our table on the formula sheet, so we have a p-value of less than, and in our case, 0.005. It's fine. They just have more precision, that's all. At a 5% significance level, which means what? It means alpha is 0.05. What's the conclusion of the hypothesis test? We already decided that we're going to reject H naught, which leaves us with A or B to choose from. Reject H naught, the data provide convincing evidence that the dice are fair. Well, that's not true because we found that there were inconsistencies. And so we're going to reject H naught, the data provide convincing evidence that the dice are biased, or some version of that. So there are explanations, of course, and before you all run to the casino or whatever, dice in casinos have flush faces. They filled those pips with the exact same material with the same density as the surrounding material. So it actually isn't a thing anymore. But if you're rolling dice at home, we play a lot of dice games, so comes in handy, right? Then yeah, the 5, the 6 are more likely to happen, right? If they're hollowed out like this, whereas at the casino, they're just flush. Yeah. So we've already said this. I've got time. Our conditions are independence, which is always a condition, okay? In this case, independence means that each case that contributes a count, so each roll of the die has to be independent of the other rolls, right? In this case, which is usually something that we argue, or by random sampling, we can say that we can assume independence. Now this one's a new one, the sample size condition. Each cell or each group, you have to have at least 5 expected counts in each cell. Okay. Now we had 52,000 some odd expected in each cell, and so we're safe, right? That's greater than 5 across the board. So when you're dealing with small counts, then it's a problem. Okay. Degrees of freedom has to be greater than 1, meaning, well, to get a degrees of freedom of 1, you would have 2 groups. Well, that's just a two sample proportion situation. So then you shouldn't be using chi-squared, you should be using a z-test for two sample proportions, right? So this is really saying that we have to have more than two groups. Which kind of goes without saying, so you can ignore that one. But how about another example where we don't have that even distribution, but we do have an expected distribution that we want to compare to? So I guess in the 2009 Iran election, there was lots of talk of election fraud. And so how can we analyze that? So we have two main candidates and a minor, or the minor candidates are all lumped together because they only got 30 votes. And so we've got this expected distribution of voter turnout. So what we can do is we can compare 338 out of 504 to 63.29%, right? Or the other way, 63.29 of 504 gives us an expected count, right? And so now I'm taking my 504 and I'm spreading them out according to this distribution, not just evenly anymore, but according to this distribution. So we've got this expected distribution and our observed counts. Our hypothesis, null hypothesis is the same. The observed counts follow the same distribution as those reported votes, right? Follow the expected distribution. And then the alternative hypothesis is that they don't follow the same distribution as the expected or the reported votes. You have to do a little bit of work to find those expected values, right? And what we said was, okay, if I'm expecting 63.29% of 504, I can do the math and I can find that I'm expecting 319, but I saw 338, right? I'm expecting 172, but I saw 136. So now I have observed counts and I have expected counts. They should all add to 504, those expected counts, right? I'm just taking 504 and I'm spreading them out as I expected to see them. Observed minus the expected squared divided by the expected for each of these gets me a chi-squared of 30.89. This is an accelerated version. What's my K here? K is 3, right? I've got 3 groups. So I have 2 degrees of freedom. Sometimes we write it in a little subscript down here. Chi-squared with 2 degrees of freedom is 30.89. And from our formula sheet, we've got that little table that we'll use. I'm gonna add a page here. If I have 2 degrees of freedom, I'm on this line here. 30 is my calculated chi-squared. So my chi-squared calculated is 30.89. 30.89 is off the charts, right? And so all we can say is that the p-value is less than 0.005. So the probability that chi-squared is greater than 30.89 is less than 0.005. What's the other way that you could do it? You could find the critical value, you could force the area in the tail to be 0.05. Any chi-squared greater than 5.99, you're going to reject H0, right? So here, Or the chi-squared critical is 5.99 if alpha is 0.05. Either way, chi-squared calculated of 30.89 is greater than the chi-squared critical of 5.99. So I'm going to reject H naught. This p-value, oh, the p-value is less than 0.05, which is less than 0.05. So I'm going to reject H naught either way. They should match up. They're doing the same thing. Yeah. No, you're welcome to use whichever one works for you. Yeah, whichever one you prefer, but I want to introduce them both. So we have both, but you only have to use one. So our conclusion, you're going to reject H naught, which is only A or C. The p-value is low, H naught is rejected. The observed counts from the poll do not follow the same distribution as the reported votes. That sounds good. The observed counts from the poll follow the same distribution as the reported votes. I'm going to go with A. This 6.4 is optional for your reading pleasure, because I guess next week we're going to start inference for means, numerical data. Exciting. Yeah. So I'm not going to do chi-square test of independence, but maybe it'll make a good bonus question. All right. If you have any questions, let me know. Otherwise, I'll see you on Monday. Let me just stop this here. There.